Alrighty, hello adventurers, and welcome to the last video of the last floor of this data structures course. I can't believe we have made it this far. Um, Thank you so much for joining me on this descent, if you will, into the depths of the data structures dungeon. It has been an honor and a privilege to get to walk you through this material, and I hope it's been an enjoyable way to tackle this subject. Now, the main thing here is that is really going to be the lesson of depth first search ordering. That's how we're going to wrap up here today. So when we think about breadth first search as compared to depth first search, they are really the same search, just using a different container. If we imagine a first in, first out queue, we can progress level by level. If we imagine a last in, first out stack, we can plunge down one path to its end, and then we can backtrack and continue on. This is the same map and the same start. We're going to utilize the same visited set in this way, but it will produce a different order. Okay, when we use the cross command and we put the BFS flag versus the DFS flag, that contrast is really the whole point of this video here to showcase. Now, depth first search must use the explicit stack. So utilizing the push start and pop. If something's unvisited, we need to mark and record it, and then we push any unvisited neighbors. There is not a recursion happening in this case. Okay. Now, what we need to do is bring the stack back. So if we remember, if we go to our hero stack header file, okay, and if we remember our stack interface here, just wanted to pull this up on screen to kind of jog our memory here again. This is the same stack you built all the way back on floor 6. You push onto the top of the stack, you pop off the top, therefore it is last in, first out. Okay. In the last video, our breadth first search ran on the queue, which was first in, first out, and it came out in that concentric ring type of pattern. Today, we're really just going to change one thing. The container, and the search will instead plunge instead of fan outwards. And so here's really the recipe, and notice how close it is to breadth first search. We push the start, and then we loop. The top tells you the room, pop takes it off. This is the same ask and then remove two-step in the last video where we were working with front and DQ. And if we haven't visited that room yet, we mark it and record it. And then we push its unvisited neighbors. Since it is a last in, first out, the most recently discovered room is going to be the next one we explore. So we end up diving down one passage and one off of that and one off of that until the end before we ever come back for a branch that we passed along the way. Okay. So this is just a callback here. We can close this stack header now. And really, we need to just scroll down in our graph header file. Okay, and we want to go down to our DFS order here. And so right here for me, this starts on line 363. Okay, so what do we need to do here? Well, notice here it takes a const reference to a string here called start. And in here, we're going to need to get us a standard vector of a standard string type, and I'm going to call it order. And then I'm going to say if not has room of start. So if it does not have a room, we return the order. That's our check. Otherwise, we're going to create a stack here that holds strings, and we'll call it the frontier. Same type of nomenclature that we did in the last video. And then I'm going to create our unordered set. Okay. Once again, of type string. And this will be our visited set. And then we will begin by pushing onto the frontier our start. And then we will enter into our while loop. And we'll say while not the frontier is empty, we'll break into it. So put our curly brace to jump into the loop. We'll create a const string. and we'll call it here, which is equal to the top of our frontier. We will then pop off the top, so frontier.pop. And then after we frontier.pop, we will have us an if branch. So I'll say if the visited.count here, we will continue. So what that means is, hey, try to push twice there, i.e. we've already visited, so just continue on to the next iteration of the loop there. Otherwise, we will say visited.insert here. I misspelled that. Let me add an extra I right there. Visited. And then we will say order.pushback. We'll push back onto order or here. And so we need to, essentially what we're saying here is we need to record on our visit, right? Or record on our pop, essentially. And then we'll say for, and we'll create a little for loop. I'll say this will be a const standard string. Put an ampersand there. Next, through our neighbors here. So get our neighbors. And then within this for loop, we'll say if not visited.count next. We'll say frontier.push next. We'll pop out our first 3 curly braces here. And outside this third one, we'll say return order. So there is our body of our DFS order function. So really in your mind, hold the last video's BFS order next to this because they're twins in essence. Same output vector, same visited set, same loop over the neighbors. 2 differences. 1, the container is a stack, which is from floor 6, so it's not a queue. And 2, with a stack, we check visited. Notice we check visited when we pop, not when we push. Now here's why. A room can get pushed onto the stack more than once, pushed from 2 different neighbors before we ever pop it. So we guard at pop time. We read the top room and pop it, and if we've already visited it, we skip with continue. Otherwise, we mark it as visited, record it in the order, and push its unvisited neighbors. The visited set still does the same job it did in the last video. It's what keeps the entrance goblin skeleton cycle from looping on forever. We pop a room we've seen, skip it, done. And this is the whole lesson of the floor. BFS and DFS are the same search, right? The only difference is whether the rooms to visit live in a queue or a stack, okay? So now that we have this built here, let's go ahead and build our executable, okay? Perfect. And so we will say self-test crossing. You see now we have all phases are okay. So the haul is now complete. We have 6 small bodies, the last code that you wrote in this dungeon. Phase 6 confirms DFS order visits depth first over the stack, every room exactly once. Okay. So there's no repeats even with the cycle. Okay. Now the demo here, we should be able to say cross from the entrance with depth first search. Okay. And you see we go down entrance, skeleton, necrothal, lich, stair, frostmaw, wraith, shadowhound, and goblins. 9 rooms reached deepest first. So we notice here that it plunges. We go to the entrance, then the skeleton, then the necrothal, then the lich, then the stair, right? It dives all the way down one path before it comes back up for the wraith, shadowhound, and the goblin. Okay. So you can kind of see if we then said, okay, well, let's do our cross entrance BFS. Notice that it is a different output. Okay. So you can see that it is different here. And the only thing we changed was the container in essence. And now to end this all off, let's do us a little benchmark of our crossing. And so what this is going to do is this is really just showing us a race. 2 ways we could store the same map. Cross breadth first at 4 sizes. Now, of course, your run can differ a little bit in terms of time, but the important thing is the shape here. Okay. Look at our matrix column. We have 50 rooms, 200, 800, 3,200, and the time will climb up steeply. Each could quadruple. Each quadrupling of the map multiplies the time, roughly around ninefold or more. That can be, average out to be a big O of V of squared. A matrix reserves a slot for every possible door, so finding one room's neighbors means scanning a whole row of V. Now, our list column, the reference adjacency list, it stays nearly flat because it stores only the doors that exist, and a crossing costs big O of V plus E. That's the lesson in a nutshell. On a sparse map, the list is what scales. Okay. Now, of course, you can notice here, like at small v, our graph does not do as good, obviously, than the matrix, right? You notice there, like at the small size, it's actually not as good. That's really the big thing. There is really just a constant thing there. The graph is keyed on string room names. So every step pays for string hashing and name comparisons that the index-based reference list doesn't. But as V grows, you'll notice that the matrix ends up getting to be a lot worse even than our graph right there. And so the reason is because it's on the list side of the contrast, that O of V plus E. And the matrix O of V squared ends up running away from it in the long run. The takeaway isn't that the graph we built is the fastest thing or the sleekest thing ever. It's really looking at complexity classes. Your list is big O of V plus E beats a matrix of big O of V squared on a sparse map. And our graph rides more on the list side of those things there. Okay. So, pretty awesome. Now, when we think about this, the map is sparse. So we think about a few doors per room, not a door to every other room. And remember, an adjacency list stores only the doors that exist. Okay. So that's really the overall thesis for what we were trying to get at here. And this is the last performance lesson of the course. So when we think about all this, hopefully this was a helpful way to close out. You've talked about all sorts of different topics with regards to data structures and algorithms, and hopefully you feel a lot more comfortable talking about these things and encountering them in your own work or other classes. And I hope you see now that you can take these tools and build upon this, and don't ever feel like even though something may seem complicated at the beginning, that you can't rise to the challenge. And I hope that this was a class that helped you feel that way. So I guess this is Dr. Joe signing out from the dungeon. It has been a pleasure, my adventurers, and I hope to see you around the tavern, waiting for our next grand adventure. It's a pleasure as always, and I'll see you soon. Bye-bye now.